So if I say first times the derivative of the second plus the second times the derivative of the first, you get this. Yeah, that's fine. B. So we're given f of x equals e to the x minus e to the minus x divided by 2. This is the same as a constant times our function. So this is going to be the same as a half times e to the x minus e to the minus x. Okay. So then my f prime is going to be my constant times my derivative. So this is going to be a half times derivative of e to the x is just e to the x. So that derivative is just e to the x. And then okay, so you have the derivative of a minus e to the minus x. So that's going to be, it's still going to be a minus e to the minus x times the derivative of the exponent. It's just going to be a minus 1. So yeah. So then when you simplify it, you get okay, yeah. So you have 1/2 e to the x plus e to the minus x. Only reason we can't add these two exponents because you have an x here and then you have a minus x here. So you have x and then 1 over e to the x. So you're not going to add those. So let's see what's on C. Okay. So for C, you can do one of two things. So my C is f of x equals e to the x divided by x. I don't want to find f prime. I'm partial to rewriting this as x to the minus 1 times e to the x and then using the product rule. But then you have to keep track. You have to be able to go back and keep track of those denominators. So in this case, I'm just going to do the quotient rule. So my f prime, again, the quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom, all of the bottom squared. So quotient rule is going to be the bottom times the derivative of the top is just e to the x minus the top times the derivative of the bottom is 1, so times 1, divided by bottom squared. Okay. If you would stop there, that would be fine. But you could also notice you have a factor of e to the x in both of those. So then you can rewrite this as e to the x times x minus 1 divided by x squared. But again, even if you stopped on that line, that would be sufficient for me. Our D, we have f of x equals x e to the x minus e to the x. So then we want to take the derivative of this. So then we have f prime is going to be, again, for that first part, you should see the product rule going on there. So that's the first times the derivative of the second plus the second times the derivative of the first. So my first is x times my derivative of the second is going to be e to the x plus my second times the derivative of my first, which is a 1. Now, the derivative of that second part is a constant times your function, so the derivative is just going to be the constant times the derivative. So the derivative is going to be still going to be a minus 1 times the derivative of e to the x is just e to the x. Notice you have e to the x minus e to the x, so this is canceled by this, and you're just left with x e to the x. Okay. So I think this notion for taking a derivative of exponential is not really all that bad. Like, it's, as long as you know how to take derivatives and you see that the derivative of e is itself, then the notion of taking these derivatives is not bad at all. Okay. Let me see. Okay. So example 4, this is analyzing a catenary. When a telephone wire is hung between two poles, the wire forms a U-shaped curve called a catenary. I don't know how to say that one. But for instance, the function y equals 30 times e to the x over 60 models plus x to the minus plus e to the minus x over 60 for x in between negative 30 and 30. This models the shape of the wire strung between the two poles that are 60 feet apart, where your x and y are measured in feet. Show that the lowest point of the wire is midway between the two poles. And then the final question is, how much does the wire sag between the two poles? So we have this U-shaped curve that's modeled by this equation here. It says show that the lowest point on the wire is midway between the 2 points. So what this does is tells us the height of the wire at any given x value. Okay, so if we want to find the lowest point on the wire, that means we need to minimize that height y. Okay, so if the height of the wire is modeled by this equation y, and we want to minimize this height, that means we need to look at, use our optimization notion, where you look at your first derivative and find the minimum, find that critical number that you think is a minimum. So take y prime, set it to 0, and solve for x. And then